Well, welcome everyone to Calculus Notes 1.2. Today we're talking about finding limits graphically and numerically. So first, just a short introduction to limits here. We have an informal description of our limit, and it says if f of x becomes arbitrarily close to a single number L as x approaches c from either side, the limit of f of x as x approaches c is that number L. And here we can see the notation for what we're going to be using here with limits. So this is the limit as x approaches c of the function f of x equals L. So let's kind of look at this graphically and see what we mean. So a limit is the intended height of the function at a given value of x, whether or not the function actually reaches that height at the given x. So I'm just going to draw a curve over here. It can be any curve. And this is going to be our function of x. And we want to find the limit of our function as x approaches this value called c. Okay, so we just trace this up and we look at the height, or the intended height, of this function at that point. And if we map this over to our y-axis, we get a y value, and that we call L, which is the limit. Okay? So what's happening here is we don't care what this value actually is. Rather, we care at what value are we getting close to as we approach this x value from both sides. Okay, so as we get closer from the left and from the right, what value are we getting closer to? And that's our L value. All right, so let's try an example here. First example says estimate each limit numerically and graphically. Okay, well let's go ahead and just do this graphically first. So here we have the limit as x approaches 1 of x cubed minus 1 over x minus 1. Now we can see from this, when we look at the domain, that x can't equal 1. So you're going to see this a lot with limits, that we're going to say that as x approaches 1, but notice x cannot equal 1. So it's really going to force our thinking with limits here. So let's go ahead and find 1 on our graph. So this is your c value right here at 1. And we'll trace this up. Now in a lot of graphing programs, when there's a hole in the graph, it doesn't actually show it because the limit exists. And when you're dealing with pixels, it's very hard to show where one single point doesn't exist. So we're going to add that in, that there is a gap or a hole right there. And here's the rest of our function. Okay. So what we're trying to do is determine, as x gets closer and closer to c from both sides here, what's the intended height? Okay. What are we getting closer to? And you can see it traces over here to 3. So for this, graphically, it looks like L, or our limit, is going to equal 3. So now we're going to try this numerically. And to do this, we're going to use a table of values, just like what we have here. Now, right in the center of the table, we're going to put our c value, which is 1. Now notice we can't actually find f of 1 because it doesn't exist. So we're not really going to worry about anything that goes in this box right here. Okay, we're not going to worry about that for now. What we're going to do is make our x values arbitrarily close to c. Now it's kind of funny because we're going to want to start over here and work our way in. and start over here and work our way in. So this is going to be x approaching 1 from the left, and this is going to be x approaching 1 from the right. So we can start out here with something like 1.5, and then we're going to march closer to 1. And we'll try 1.1, we'll do 1.01, and 1.001. So we're within 1,000th away from our intended C value. Now, of course, you can get smaller than this, but we'll see if this turns out to be good. So from the left, we're going to just do the same intervals, but now going below 1. So here we're going to start at 0.5. We'll jump up to 0.9, 0.99, and 0.999. So again, we're 1,000th below 1. So here you can see numerically our x values are approaching 1. So what we want to do now is figure out what are our y values doing. Okay? So what is f of x approaching as we get closer here? And that's what we're going to try to answer. Okay, so we're going to use our table of values for this. So pull out your calculator. Okay, and in y equals, we're going to put in our function f of x. So we have x cubed minus 1, and then divided by x minus 1. Okay, we could graph it and we would see the same graph over here. Okay, so just to verify that it is the same. But we really want to focus on our table of values now. So because we are choosing what our x values are, we need to set up our table a specific way. So we're going to set up our table first, and we'll only have to do this one time for this lesson. So you can see the table set right here. So you need to push your second button, and then second table set. And you need to change the independent variable to ask. Okay, so if you scroll down, you can hit enter, you can see there it's on auto, and then you can hit enter and it'll be ask. So it'll be darkened around what you want. Now we're going to go ahead and go to our table of values by pressing second table right here. Now I already have values in here. You may or may not, and it doesn't really matter. We can clear them out by hitting delete. Okay, now we have a blank slate. So we're just going to type in these x values now, and it's going to spit out the y values, or f of x. So 0.5, 0.9, 0.99, 0.999. Okay, so we're just going to record these right here. 1.75, 2.71, 2.9701, and 2.997. Okay, now let's go ahead and try it from the right side. So 1.5, 1.1, 1.01, and that's all it gives us there. So you're going to have to go up and replace another one. Okay, so for 1.5, we get 4.75. For 1.1, 3.31. For 1.01, we get 3.0301. And and for 1.001, we get 3.003. So looking at the trend here, as we approach from the left and from the right, what value is f of x getting closer to? And it looks like it's getting closer to 3. And so we're just going to put 3 there as our final answer. All right, I want you to go ahead and try example B on your own. You're going to follow the same steps. You're going to find the limit graphically, just like we did up here. Then you're also going to find it numerically right here. You can pause the video and come back in a second to check your answer. All right, welcome back. Let's go ahead and check your answer here for letter B. Okay, I have here that the limit as x approaches 0 of this function is 2. And you can see this graphically. As we approach 0 from the left and the right, we're approaching 2. Now hopefully you did find that x can't actually equal 0 in the domain, because that would give us 0 in our denominator here. So should have this open circle right there. Okay, so graphically it looks like L is 2. When you try this numerically, again you should have 0 here. I decided to choose these values. Okay, you can choose whatever you like as long as they're getting closer from the left and closer from the right. And then if you look at these, 1.99, so on and so forth, and 2.00, they're all going towards 2. That's how you get the limit of 2. For our next example, our function looks a little bit funny. So we're just going to define f of x as 1 where x does not equal 2 and 0 where x equals 2. Okay, so right here at x equals 2, we know our function equals 0 because it tells us. And we know where it doesn't equal 2, our function equals 1. So it's going to look like this. Okay. We are going to put an open circle right there because at 2 it jumps down to 0, and then after 2 it jumps right back up. Okay. So in this we want to find the limit as x approaches 2 of our function f of x. Now this example is really going to highlight our key concept here, that the existence or non-existence of f of x at x equals c has no bearing on the existence of the limit of f of x as x approaches c. In other words, it does not matter what's happening at x equals 2. All we care about is what's happening going up to x equals 2. So graphically, okay, if we were to trace along this as we get closer and closer, what is the value we're getting closer to? Well, that value looks to be 1 from the left and the right. If we were to try this numerically, we'll put our c value right in the center there. And we can pick some values that get larger here, and then we'll pick some values that get smaller. Okay, so if x is 1.9, what is f of x? Well, if we look at our function, anything other than 2 is going to yield 1. So we know all three of those equal 1. When x equals 2, we know f of x equals 0. And if we're at 2.01, we're right back to 1. Okay, so again, as x approaches 2, from the left, and x approaches 2 from the right, what's happening to our f of x value? Well, f of x is approaching 1 from the left, and then from the right, f of x is also approaching 1. Notice, even if we made even smaller difference in here, 2.0001, we're still going to get 1. And so our limit here, as x approaches 2 of f of x, equals 1. So just to review, in looking at our limits here, doesn't matter, in these two cases, f of x didn't exist at that x value, okay, but we still have a limit. In this case, f of x did exist, but it had nothing to do with what the actual limit was. All right, it's a very important concept as we move forward here. So if the existence or non-existence of f of x at x equals c has no bearing on the existence of the limit of f of x as x approaches c, what does create a non-existence of a limit? And that's what we're going to talk about in this section, is limits that fail to exist. So there are 3 common types of behavior associated with the non-existence of a limit. The first one is that f of x approaches a different number from the right side of c than it approaches from the left side. Okay. The second one, f of x increases or decreases without bound as x approaches c, thus yielding a non-real number. Or f of x oscillates between 2 fixed values as x approaches c. So we have 3 examples here that are going to show these 3 types of behavior. So for our first example, it just says show that the limit does not exist. So here's our graph. And here is the equation we're looking for. So it's finding the limit as x approaches 0. So here's c equals 0 of the absolute value of x over x. Now in this case, it looks like x cannot equal 0. Okay, because then we'd have to divide by 0. So graphically, if I were to look at this, as I approach c from the left, this looks like it's giving me an L of -1. But as I approach c from the right, looks like it's giving me an L of +1. Okay, so that right there is going to tell me that the limit doesn't exist. If we look at our table of values here, we'll put 0 here in the middle. Get larger and then get smaller. Okay, if we examine our equation, so it's going to be the absolute value of x divided by x. So when x is negative here, it's automatically going to make the numerator positive, but the denominator is going to stay negative. And since it's the same thing, we're going to get either positive or -1. So if x is negative, then we're going to get a -1 right here. Now if x is positive, then it's just going to stay +1. So you can see numerically from the left side, f of x is getting closer to -1, and from the right side, f of x is getting closer to +1. So for our answer, we want to explain this a little bit. We want to say the limit doesn't exist because f of x approaches a different number from the right and left of c. So you do want to give a little explanation, and that highlights our first point right up here. All right, let's move on to our second one. Example B. Here we have the limit as x approaches 0 of 1 divided by x squared. So you can see here the graph of 1 divided by x squared. And again, because pixels have a thickness, a lot of times your graphs don't become very clear. But we would see that there is an asymptote right here, that our y values can never go below 0. And we'd also see in the domain, because of the x squared, that x can never equal 0. So graphically, what's happening as we get closer to our c value of 0? Well, from the left side, it looks like this graph is just going to keep shooting up to infinity. And from the right side, the same thing. Okay, so even though they're going in the same direction here, this is increasing without bound. So graphically, it looks like our limit doesn't exist. Let's go ahead and show this numerically as well. We'll put 0 here in the middle. And just standard, I usually use these. And again, we can use our table of values if we're not good with using these numbers here. So 1 divided by x squared. And then again, I'm going to push second table. Type in negative 0.1, negative 0.01, negative 0.001. Okay, so we get 100. And then we get 10,000. And we get 1e6. So we're going to come across these exponents a little bit here. 1e6 just means add 6 zeros after the 1. So 1, 2, 3, 4, 5, and 6. Now, will we ever get to 0? Okay, we said no, we won't, because it's x over 0. However, that is not what causes this limit not to exist. Okay, we'll move on to the right side here. 0.001, 0.01, and 0.1. Now we get 1e6 again. So that's 1 with 6 zeros. .01 gives us 10,000. 0.1 gives us 100. So you can see as we f of x from the left side is increasing without bound. So it's going to get larger and larger and larger. It goes to infinity. Here, from the right side, the same thing is true. So f of x is going to increase without bound, going towards infinity. Now it turns out infinity is not a real number. Therefore, the limit does not exist. So we're going to write the limit doesn't exist because f of x increases without bound as x approaches 0. So this one was our second type right up here, increases or decreases without bound. We're going to look at a very interesting function, sine of 1 over x. So this is what it looks like on my computer. We just kind of, the graph comes down, goes up to 1, goes back down to -1, and then as we go through here, it just starts going crazy back and forth between 1 and -1. And then as it gets a little bit past 0, the same thing happens until it sort of starts to level out and keeps on going. So we have this oscillating behavior between 1 and -1. And that is going to make the limit not exist as x approaches 0. Now for these ones, we're not actually going to use a table of values. You can look in your textbook if you're interested about that, but that's going to be outside of what we're going to be doing here. So for now, you can just say limit doesn't exist because the function oscillates between 1 and -1 as x approaches 0. And you can leave it at that. Alright, so we've dealt with an informal definition of a limit and seen how we can find it graphically as well as numerically. We've also seen where a limit does not exist. And now we're going to move on to the formal mathy, very mathy definition of a limit. Okay, so don't get too freaked out. Hang in there and we'll be all right. So our informal description, which might be mathy enough for you, was if f of x becomes arbitrarily close to a single number L as x approaches c from either side, the limit of f of x as x approaches c is L. So that's exactly what we've been dealing with. Now let's kind of break this down and see what this means. So this first part here, f of x becomes arbitrarily close to a single number, means that f of x lies in the interval L minus some epsilon, comma, L plus some number epsilon. Here's what that looks like. Let's just draw a straight line as our function. Why not? And we'll choose this point right here as our limit. Okay, so again, this is the point C, comma, L. We can see where this maps onto the x-axis, then onto the y-axis. And we get L here. Okay, so this first part, if it lies in the interval L minus epsilon and L plus epsilon, that's basically talking about a distance where our f of x is going to be within epsilon units of the limit. Okay, and we do that with an absolute value sign. So absolute value, when we're dealing with that, all we're talking about is the distance of epsilon. We're going to call this arbitrary number L plus epsilon. We're going to call this number L minus epsilon. Okay, so what that means is this length right here is epsilon. Above it and below it, and it gives us these 2 points, L minus and L plus epsilon. Okay, and that's what it means to say f of x becomes arbitrarily close to a single number. It means it's somewhere in between here. And that's all we're talking about. Now, the x approaches c portion means there exists a positive number, we'll call this delta, such that x lies in the interval c minus delta, comma c, or c, comma c plus delta. At any rate, we're going to have x minus c being between 0 and delta. So all we mean by that is we're going to take delta away from c. We'll call this c minus delta. So there exists a delta where we can subtract it there, and also where we can add it. Okay, so you can see x is approaching c, meaning we can get somewhere close enough within delta of c such that this happens. As we map c minus delta up to our function, and if we map it back over to the y-axis, it's going to give us an f of x that falls within this range. Likewise, if we map c plus delta, so delta above c, up to our function, and then we map it back over to the y-axis, that value of f of x will also fall in that range. Okay, so basically we're saying as we look at getting closer and closer to a specific number, our L, which is an f of x, there's a certain number delta that if we're within close enough to c, it's going to give us an f of x that's somewhere in that arbitrarily close range. Okay, thoroughly confused? Maybe. But anyway, this is the formal definition, and we're going to talk about how we can use this now to prove that a limit exists. Okay, so it's going to be very important that you memorize this formal definition. It's also called the Epsilon-delta definition. So if you see that, this is what we're talking about. So the limit as x approaches c of our function f of x equals L means that for each epsilon greater than 0, there exists a delta greater than 0 such that if the absolute value of x minus c is between 0 and delta, then f of x minus L, the absolute value, is going to be less than the epsilon. Okay, so whether you understand this definition or not, we're going to use it right down here in a couple examples and see how this works. Okay, so it says given the limit, okay, the limit as x approaches 3 of our function 2x minus 5 equals 1. So they're giving us the limit. They're saying the limit is 1. Find a delta such that the absolute value of 2x minus 5 minus 1 is less than 0.01 whenever the absolute value of x minus 3 is between 0 and delta. Now again, this may not mean a whole lot to you, but you need to be able to identify the different items in this from the definition. Okay, if we can do that, we'll be on a good start here. So as I look at all of this, I'm seeing the limit as x approaches 3. Well, what is 3? That is our c value. So we know that c equals 3. If we look right in here, this is our f of x. So we also know f of x equals 2x minus 5. And we're saying the limit equals 1. So 1 right here is our L. L equals 1. Now they're asking us to find a specific delta such that all of this is true when this is true. So in this first part, let's see if we can identify this as to where it fits in with our definition. And a lot of times when you do this, you're going to see this backwards. So just kind of look here. You're going to see that this left side is the right side of our definition. So we start backwards. So you can see here's your f of x, right? Which is the same here. And then minus L, you can see that there. Minus L is minus 1. And then less than. And this is less than epsilon, and here we have 0.01. So for this example, we're going to let our epsilon equal 0.01. Now, this is going to be whenever the absolute value of x minus 3. Okay, now what is x minus 3? Well, this section looks exactly the same as this one. So x minus c is between 0 and delta. So now x minus 3 is between 0 and delta. So you can see our letter C is right there. Okay, so hopefully you can understand where all the pieces of this puzzle come from. So graphically, let's see what we're trying to do here. So we're looking for our limit at x equals 3. So that's our c value. And it's saying the limit is 1. And we're going to prove that, pardon my stretching of the range here, but we're going to put our L plus epsilon right here, which would be 1.01, and our L minus epsilon here, which is 0.99. So our task is to find a delta so that when we map it up to our function, it gives us an f of x that's going to be in this range. So as we go delta below c, f of x is still going to be greater than 0.99. And as we go delta above c, it's going to give us an f of x that's going to be also less than 1.01. Okay, so this is what our task is, to find that delta. So here's how we're going to do it. What we have to do is get this portion of the equation to match this portion right here. So we have to get the absolute value of f of x minus L to equal the absolute value of x minus c. And that's our first step in doing this. Okay, so here we go. Now comes the math. So 2x minus 5 minus 1 equals 2x minus 6. That's still the absolute value, and it's still less than our epsilon 0.01. Now, with absolute value, we can factor out our constant of 2. We're left with 2 times the absolute value of x minus 3 is less than 0.01. Now, hopefully, at this point, you can see that the x minus 3 and the x minus 3 and the absolute value are the same. Okay, so that's what we want to do. Now we want to just go ahead and get the absolute value of x minus 3 by itself by dividing by 2. So we're going to say x minus 3 absolute value is less than 0.005. So that's 0.01 divided by 2. Now looking at this, okay, if we compare it right here, that is the same. Okay, do you see that? So what we've found here is that delta is going to be equal to 0.005. So that was our task, find a delta such that this was true, and we did that. Now unfortunately, we can't stop there. We have to actually verify that this works. So to be able to do that, we're just going to rewrite this second part, okay, which is actually the first part of our definition, using the delta that we chose. So we're just going to go 0 is less than the absolute value of x minus 3 is less than our delta of 0.005. Okay, so you just want to substitute that right into the second part. Now this implies, and this is going to feel where we're just going backwards. We're almost restating exactly the same thing. So this implies, and we're going to rewrite this part, f of x minus L, so 2x minus 5 minus 1, and then we're going to equate it to, well, everything that we did over here. So it's 2 times the absolute value of x minus 3. And we're going to say that's less than 2 times our 0.005. Okay, so we're just kind of undoing everything we did here. So we're going backwards. We're going to say that equals 0.01. And so here we ended with the exact same thing we began with, the epsilon of 0.01, and that's how you're going to show that this delta of 0.005 actually works. And so what that tells me here is if I pick a C value of 3.005, or if we go 0.005 below, which would be 2.995, it's going to yield my L value, or f of x value, that's between 0.99 and 1.01. Okay, so in doing this, we were asked to find the delta given a specific epsilon. Very important that this doesn't prove a limit exists. Okay, for us to prove that a limit exists, we're going to have to show that it works for any e, not just the one that they give us. Okay, because, you know, if we choose this e, well, maybe if we got a little closer, this whole process wouldn't work. So what we're going to try to do now is prove this for any e. So when we're trying to prove it, your example is going to look like this. It's going to say use the epsilon-delta definition to prove that the limit as x goes to 2 of the function 3x minus 2 equals 4. So we're going to prove here that the limit equals 4. So again, just a couple things. Go ahead and find your C, your f of x, and your L. I get c equals 2, f of x is 3x minus 2, and L equals 4. And let's begin our proof. So we're just going to start by writing for each epsilon greater than 0, because we're doing it for all of them, there exists a delta greater than 0 such that, we'll abbreviate that ST, such that, and what we want to do here is go ahead and start with our definition, but start with the second half of the definition. Okay, so we're going to write f of x minus L in absolute value is less than epsilon. And we're going to plug in everything we know. Okay, so the absolute value of f of x, which is 3x minus 2, okay, minus L, which is 4, is going to be less than epsilon. We're just going to leave that epsilon to represent anything. Okay, now this becomes very similar to what we did in the previous example. We want to go ahead and get this whole part to look like, well, what are we trying to get it to look like? Well, when 0 is less than the absolute value of x minus c, so we're just going to take this whole second part, okay, right from here. So we have x minus c, and c in this case is 2, is less than our delta. So what we're going to do now is go ahead and figure out what delta is in terms of epsilon. So we're going to try to get this absolute value to look exactly like this absolute value right here. Okay, so this becomes 3x minus 6 less than epsilon. We can factor out the 3. And then divide the 3 to the other side. So we get the absolute value of x minus 2 is less than epsilon over 3. Now again, because these two things match, okay, we can say that x minus 2 is less than delta, and so we can equate delta equals epsilon over 3. Okay, now that was just our first step in finding our delta. Now we're actually going to prove that it works for each epsilon greater than 0. So this is where we just rewrite this statement replacing our delta. Okay. So we write 0 is less than the absolute value of x minus 2. It's less than, replace our delta with epsilon over 3. And now we kind of work in reverse. Okay, so at this point we're going to rewrite our original part here. Absolute value of 3x minus 2 minus 4. And again, we already know this equals 3 times the absolute value of x minus 2. And this is less than 3 times epsilon over 3, which just equals epsilon. So what we've done here is we found delta is epsilon over 3. When we plug it back in here, epsilon over 3 for delta, okay, we end up being left with just epsilon. So for any epsilon greater than 0, if this is our delta, we know we're going to get back epsilon. And so it's going to work. So graphically, Let's see what that looks like. So here's c equals 2. Here was our limit of 4. Here was our 4 plus our epsilon. Here's our 4 minus epsilon. And we found that 2 minus our delta and 2 plus our delta are going to yield y values in that range of epsilon no matter where we go. All right, nice job hanging in there. And that is the end of our notes on section 1.2. Thanks for watching.